go on to introduce the next speaker, who is Madison Feehan.
Thank you.
She is the founder of Space Copy, together with others, and she's also an employee of NASA with a background in lunar instrument development for planetary science, leading the change for STEM engagement of early career professionals. Has done a fair bit of voluntary work in different things, and she has an education based in business technology management and holds a specialization in entrepreneurship and innovation from Harvard Business School. And as always, feel free to fill in if I've missed something, and otherwise the floor, the air, and the ether is yours.
Wonderful. Thank you so much, Nicholas. Just give me one moment here to share my presentation. Let me know if everybody can see my screen.
Yes. Yes, there it is.
Excellent, excellent. Well, distinguished guests, space enthusiasts, thank you so much. And good morning, and thank you for joining me today as we delve into the exciting realm of lunar manufacturing. So I'm Madison Feehan, and as COO and co-founder of Space Copy, we are developing an additive manufacturing company that is constructing 3D printing systems to be deployed on the surface of the moon and eventually Mars. I'm super proud to be presenting today at Lunar Development Conference, and I'm excited to explore the discussions that arise for the need of manufacturing in space, the growing space economy, and the relevance of Space Copy to NASA's objectives in advancing the technological development of space manufacturing. Now, to give a bit further to my credentials before I begin my presentation, in addition to some of my work with Space Copy and my technical background, I also have experience in heliophysics and astrophysics, and I've done volunteer data analytics work for ESA, NSF, and CERN. I'm a member of a global consortium called Moontrades, which is working on developing advanced robotics systems for lunar mining and integrating AI-powered education for STEM enthusiasts. I'm a member of Women in Aerospace Canada, as well as NASA's Lunar Surface Innovation Consortium, and I'm the proud co-author of a book for artificial intelligence for Earth resource management commissioned by the White House. So I'm honored to share with you the incredible and remarkable progress that we have made and the immense potential that lies ahead for the international space community. So let us begin by exploring the concept of lunar manufacturing and unmanned missions, both in orbit and on planetary surfaces. So it's a crucial step to be able to supply astronauts both on manned and unmanned missions, even in both in orbit and on planetary surfaces. It is absolutely critical to establishing sustainable and self-sufficient human presence beyond Earth to have lunar manufacturing. Now, one of the most promising methods in lunar manufacturing is in situ resource utilization, or ISRU, which involves extracting valuable commodities from space to use as raw materials for manufacturing. Now, the moon, with its abundant resources, offers an excellent opportunity for ISRU. Lunar regolith can be extracted, processed, melted, and fused together using 3D printing and additive manufacturing technology. And these recent advancements in the industry are helping to break down some of the really critical barriers and revolutionizing our ability to live and work in space. So we are now capable of mass producing parts using these available resources on the moon, reducing our reliance on Earth for resupply missions. And that is the subject of today's topic. So many people might wonder, why lunar manufacturing? So to speak further to its value for the space economy, one must look no further than government space agencies and defense programs which are funding this exploration and development of this kind of technology. In particular, NASA has identified in-space manufacturing as an absolute critical goal of achieving a lunar habitat outlined in things like the Moon to Mars objectives, ISAM regulations, ISRU market gap assessment, and planetary decadal survey requirements. The lunar manufacturing market is currently valued at $1.5 billion US, and this is slated to increase to $7.5 billion US by the year 2030. And with an estimated target value of $1.2 trillion US by 2040, the lunar economy itself is recognized globally as one of the most fast-paced, growth-induced economic markets since the dot-com bubble. So this is where Space Copy comes into the picture. At Space Copy, we have harnessed the power of ISRU technology and integrated it into our 3D printing processes. So the cost of sending a very small payload rocket to the moon is a minimum estimated $5 million for a small resupply payload. So the high cost and high risk factors of sending constant rockets to space present an active challenge for living on the moon when you are dealing with mission critical life and death scenarios. So Space Copy is going to provide you with one of the most essential parts of the space ecosystem. We are transforming human exploration methods by disrupting the way that we sustain human presence on the moon and eventually Mars. Solving the challenge of sustainability is part of our team's vision. Our mission is to create sustainable parts for a variety of applications using lunar regolith as the primary material. By doing so, we are not only reducing the cost and complexity of space missions, but we are also paving the way for long-term human habitation on celestial bodies like the moon and Mars, while also providing a rapidly deployable in situ method for reducing the high risk and high cost of frequent payload resupply missions to the lunar surface. So our novel technology is changing the game of how Earth to Moon supplies transportation is delivered by developing a lunar manufacturing device, an ISRU mechanism on the lunar surface itself. The Space Copy 3D printer is a lunar manufacturing plant, research bank, and testing lab all in one, utilizing those lunar resources to 3D print all of the supplies and infrastructure needed to sustain human life on the moon through 4 simple steps. First is sampling of regolith using a laser spectroscopy system to determine its mineralogy. Then we have a custom mixing process that helps you create a blend of high durability for manufacturing. After that, we're using our selective laser melting process to 3D print our parts. And finally, we are integrating an AI and machine learning software that will provide you analysis for future missions and allow you to telecommunicate your data back to Earth for scientific research. The heart of this project is understanding why Space Copy is different compared to other manufacturing technologies currently being employed. So Space Copy is the first lunar instrument that is capable of combining multiple technologies into one device using our selective laser melting process, which is regarded as top tier in the industry for many reasons. Mainly, we're able to produce really complex geometries without any kind of external support, and therefore no post-processing is required either. Furthermore, all of our prototypes are reusable and recyclable, which largely plays into the sustainability factor of our innovation. And to speak to it even further, we are a patent-pending technology, and we have applications for Earth-based use as well. Space Copy is committed to incorporating cutting-edge technologies into our manufacturing and testing mechanisms. We're integrating things like solar power, AI, machine learning, laser spectroscopy, and advanced telecommunications software to deliver a high-efficiency manufacturing system with numerous applications for living in space and conducting Earth-based research in extreme environments. Right now, we're right in the heart of our research and development stage, and our goal is to establish a robust infrastructure for the production of vital components, equipment, and tooling in space, ensuring the sustainability and success of future missions, while saving a minimum estimated $60 million annually that can be reinfused in the economy that would otherwise be spent on resupply payloads. While doing this, we are also contributing to compelling scientific research that will help us understand more about the planets of our solar system and how we can optimize spaceflight for generations to come. And this is one of the critical reasons why lunar manufacturing is so important. You're not only solving the difficult challenges for inhabiting other planets, but you're also saving money and collecting data for STEM research that's going to provide you with an absolutely critical analysis of how we can use the lunar surface for future generations of spaceflight. Our current progress is at a technology readiness level 3 and a market readiness level 4, which basically outlines that our project is in its prototyping stage with a proven concept aligned for success. You can see on the screen here a lab demonstration of some of our early stage prototypes, which are bricks for habitat construction. Aside from bricks, we're also looking at creating repair parts, rovers, simple tools, piping for infrastructure, as well as things like launch pads. So moreover, we have recently been awarded with 2 grants, one from the Saudi Space Agency in partnership with Techstars and the other a NASA Phase 1 grant. And we are working to form several partnerships with clients and industry leaders. We are proud to have the support of many leaders in academia, industry, and government who are supporting our initiatives, some of the names in which you can see here on the screen. We have also recently filed applications for some other NASA grants, including a NIAC grant and NASA HeroX Entrepreneurs Challenge, and we do have some confirmed LOIs and partners, which is excellent. Now, to speak to the viability of space copy and lunar manufacturing as a monetizable market, the market strategy defines that the total projected market will be around $7.5 billion by 2030 just for lunar manufacturing itself. And Space Copy is aiming to be the industry leader in this field. What's interesting here is that studies show for every kilogram of product developed from regolith, we can generate at least $43,000 in revenue that private and government-based institutes plan to use for scientific study. And we will be monetizing our services through product sales, rentals, contracted experiments, Earth-based manufacturing, and educational workshops for STEM students and industry professionals alike in order to facilitate a higher understanding of what lunar manufacturing is and really engage the community in the importance of space science and developing new cutting-edge technologies. Now, to speak quickly to our team, we have really diverse backgrounds in engineering, aerospace, and business, in combination with our distinguished industry advisors who bring decades of experience in both space tech and entrepreneurship. And we are very excited to be able to provide this technology to support the next generation of spaceflight to the moon and beyond. So if you would like to learn more about what we're doing, you can visit us at spacecopy3d.com or by following at spacecopy on social media. So to continue forth now with the secondary part of my presentation, NASA's goals of developing an advanced lunar habitat, the implications of lunar manufacturing and the growth of the space economy are far-reaching. As we push through the boundaries of space exploration and colonization, we are witnessing the rise of a new era, this flourishing space economy. And this economy encompasses a wide range of industries, including manufacturing, resource extraction, telecommunications, tourism, and research and development, as well as many more. And the space economy not only drives innovation, but it also presents us an exciting opportunity for economic growth and international collaboration, which is one of the main features why space exploration is so important to people like NASA. The Moon to Mars architecture, developed by NASA, chronicles this technical development, and the Exploration Systems Development Mission Directorate, or ESDMD, is the primary body of research that is coordinating the implementation of this program, which is also responsible for influencing public policy on space and engaging with international communities and other space agencies, academic institutes, and private commercial industries who would like to become engaged with NASA. More specifically, the objectives spend a very significant amount of time explaining the technologies required to facilitate responsible space exploration, and lunar manufacturing encompasses over 14 sections of the paper, which speaks to its importance both by government and by private industry. Now, through our work at Space Copy, we are also addressing and aligning with NASA's Planetary Decadal Survey. The most recent version of this survey was released this spring, done every 10 years. This one spans from 2023 to 2032, with objectives to improve the technological development of space manufacturing, as well as other kinds of hardware and software that will be required to facilitate manned missions. By leveraging the potential of lunar manufacturing in ISRU, we are enabling NASA to establish sustainable infrastructure on the Moon and Mars. And this infrastructure will support future missions, enhance scientific research, and provide a stepping stone for ambitious endeavors, such as crewed missions to Mars, which anybody in the space industry knows, it is the buzzword when it comes to space exploration. So, as referenced earlier, another key point of interest is the United States Department of Defense In-Space Servicing Assembly and Manufacturing Program, also known as ISAM, which has the goals of advancing research and development in space, prioritizing the expansion of scalable infrastructure, and accelerating the emerging ISAM commercial industry. Now, aside from the Department of Defense, these undertakings are also being led internationally by public government agencies, such as the Canadian Space Agency's LEAP program, European Space Agency's Open Space Innovation Platform for ISRU, as well as JAXA and the Japan Gasoline Company's ISRU plant program, as well as a whole bunch of private commercial industries who are also attempting to explore these regulations and help monetize and expand the commercial development of manufacturing and other space hardware. So to further aid this research, products such as the development of lunar regolith simulants have played a critical key role in understanding how in-space manufacturing can be achieved. I know we've had some wonderful speakers so far today who have given a really complex overview of regolith for ISRU purposes, so I will keep things high level. The accuracy of these simulants provides really critical assistance to understanding the mineralogical properties and thus the manufacturing parameters of regolith. That being said, there is no 100% accurate lunar soil. So that begs the question, how are you able to use regolith simulant for testing purposes? Some of the strides that are being developed by places like Exolith Labs in partnership with Kennedy Space Center and University of Central Florida, as well as other key players like Colorado School of Mines and some of the international regolith simulant developers, are looking at advancing the technical capabilities of the simulant to include a more accurate mineralogical as well as particle size distribution of the regolith simulant in order to help aid its actual accuracy to the soil itself that you would find on the moon. And right now we're working with around a 99% accuracy for some of that Highlands and Mare simulant, which is allowing us to be able to conduct some of our R&D testing much more efficiently. And now that we are familiar with the importance of lunar manufacturing, we must turn to understanding the deliverables which are required to achieve a congruent space mission. And that is including things like infrastructure development, such as launch pads, roadways, and piping, as well as supply chain management, such as repair parts, simple tools, and bricks for habitats. And the best part of lunar manufacturing is once you are able to establish it, whether that's cislunar or in low Earth orbit, you are able to apply it in a variety of different manners. You can have it operating in orbit on the International Space Station, such as the strides being made by companies like Redwire. Or you can even choose to have a mobile version, such as placed on a rover. So this basically follows the primary technology that we are addressing at Space Copy, and these are just some of many key deliverables that will be answered by lunar infrastructure development. So this technology has sparked the interest of multiple private organizations. Some of the larger industry leaders like SpaceX, Blue Origin, Axiom Space are already making developments in this, while some of the medium-sized companies like Lunar Outpost and Maiden Space, as well as many more, are actually exploring this as a viable long-term concept. And with the addition of companies in lunar mining and excavation, it is clear to see why lunar manufacturing is not just a visionary concept, but in fact, a reality for developing and sustaining a lunar colony, because we are able to really create this back-to-back supply chain from mining to excavation to manufacturing to eventually habiting the space environment. So in conclusion, lunar manufacturing powered by ISRU holds the key to unlocking the full potential of space exploration and habitation. So companies like Space Copy, with its innovative use of 3D printing, AI, machine learning, laser spectroscopy, and more, are at the forefront of this transformative journey. And together with NASA and other visionary partners in government, industry, and academia, we are shaping the future of manufacturing in space, fostering economic growth, and expanding the horizons of human exploration. And I welcome each of you to be a part of our journey, because in order for us to achieve this goal, we are going to require the influence of many subject matter experts, and we more than welcome the fostering of international community. So thank you so much for your attention, and I look forward to answering any questions that you may have, and let us embark on this incredible adventure together as we pioneer a new era of space manufacturing and exploration. And if you'd like to get in touch with me after the conference, you can take a moment to take a quick snapshot of my email address here on the screen. So I look forward to the Q&A part of today, and thank you very much.
Thank you very much as well. And we do have some questions here. Let's see, Marufa wonders if SpaceCop is part of NASA or a separate private entity.
Oh, thank you for the question. Yes, we are a separate private entity.
Want to develop that? Or yeah, that's a good answer to the question, obviously. Okay, Marufa Bian says, thanks for mentioning NASA's decadal survey. Very important. We recently published a paper on various roadmaps for sustainable space exploration. And she's giving a link. Right. I'm not sure if that's not really a question, but if you want to comment on that.
Yeah, thank you, Marufa, for posting that link. Yes, it's absolutely critical to be talking about NASA's decadal survey. I know there's several, ranging from biological and physical sciences to astrophysics to planetary science, which is where we're focusing our main efforts. So yes, it's very important to be including things like public policy when you're trying to develop things commercially and privately. So thank you for pointing that out.
So the regolith that you use as your feedstock, does that need to be processed first, or is it raw regolith right from the ground?
It's taking that raw regolith straight from the ground. And what's interesting is part of our mixing technology before you take it to 3D printing for prototyping is you are able to scan the mineralogical composition of it using a laser spectroscopy system, and then just kind of determine, okay, what materials are you working with? And how can you optimize that if necessary for the durability and strength aspects? So if you did need to add a binder to it to increase its strength, you have the option of doing that. And furthermore, other companies that are working in conjunction to create things like metal extraction, if you're looking to add even more material to the regolith to create a more metal-based prototype, you are able to combine multiple different things to create a custom blend for your manufacturing process.
Cool. And what kind of size parameters are you looking at? Is this something that's just a couple of square meters, or can it be expanded out to make large components?
Right now, we're going to be focusing on printing small to medium-sized parts. We're working with a couple of different parameters. Our smallest version would be a minimum size of 16U for the printer itself. And then we are looking at a larger system of around 1 cubic meter. So anything that falls within those parameters is something that we would be able to achieve printing. And we're mainly going to be focusing on supplies and small-scale infrastructure.
Cool.
All right. I was a bit interesting on the database that you're building and what exactly are you putting in there? Will it be just location and composition, or will you actually perform, say, mechanical and chemical tests in order to see what it ended up like?
Well, as for mechanical testing, that's where that laser spectroscopy system really comes into play, because you'll be able to use that not only for regolith identification, but you can use it in turn for determining the mechanical properties of what you're printing. But the software itself is meant to combine AI and machine learning to determine the mineralogical composition of the regolith. So it will be scanning databases that are already publicly available about what minerals, volatiles, and compounds are in the regolith. And you also have a secondary GPS geocoordination function that will allow you to enter the coordinates of where you're extracting the regolith from, so that you can determine the mineralogical differences between different regions of the south pole of the moon.
I do get the composition part, but how do you measure mechanical properties with spectroscopy? And that sounds a bit odd.
Yeah, no, it's not standard mechanical testing. You won't be able to test things like durability and strength, but you will be able to take a closer look at the structure of the prototype itself and see where there are any strengths and weaknesses in the printing process, and in turn, how you can optimize those parameters for future tests.
Yeah, I think that's possibly a suggestion from me to put in some kind of mechanical testing in the system, because what you're dealing with on the moon is not what we are used to dealing with here. So regardless of the chemical composition, you will have different mechanical properties.
Absolutely, absolutely. Lots of factors that come into play.
Let's see, there is another question here from Mani Pimenta. We're also very interested in using Virtual Moon as a STEM platform. Would love to get in touch with you about that, as well as your ISRU research. Can take that later. Is that laser spectroscopy from orbit or done on the surface? Was his question as well.
That laser spectroscopy system will be done on the surface using a Fourier transform infrared spec system.
Right, shipped up from Earth, I assume. You're not going to make it on the moon, right?
No, everything will be shipped up and assembled from a modular structure on the lunar surface, and then all of the material itself will be provided in situ.
Yeah, that's what I got. Maybe you want to comment on the collaboration on different STEM platforms, which was his previous comment there.
Yeah, sorry, I must have missed that comment. So yeah,
we're also very interested in using from Mani Pimenta. We're also very interested in using Virtual Moon as a STEM platform. Would love to get in touch with you about that, as well as your ISRU research.
Gotcha. Yeah, no, to speak about STEM platforms that we're engaging with, so we're basically breaking it down into 3 different sectors, whether that's government, industry, or academia. And we are engaging with a lot of people to try and form these partnerships. And as for STEM platforms itself, some of my private work, aside from Space Copies, engaging with companies like Moontraits, which is something that I'm co-founding to provide an AI education platform for STEM enthusiasts who want to learn a little bit more about how to use artificial intelligence for space. So if this is what you're referring to, then yes, definitely, I would love to get in touch with you as well and talk about ISRU research and AI for space.
All right. I have a question about the durability of this machine. I guess you don't have any hard data on that yet, but what do you think? How much maintenance will the 3D printer need? I mean, there is a joke going around. Step 1, borrow a 3D printer. Step 2, print a 3D printer. Step 3, return the 3D printer. I guess that's not quite doable yet.
No, that is not quite doable yet. It's an excellent question, actually. So yeah, to speak to that whole durability process, there are some public research studies available that I would be more than happy to reference. But the actual durability of the regolith can be estimated between around 70 and 80% is what you would usually achieve in standard manufacturing testing with other ceramic similar materials. So there's a high durability of strength in what you're working with, because if you're aware, regolith has a very similar composition to ceramics. So if you're able to conduct testing with a ceramic material, you will have a really good idea of how that regolith is going to perform durability-wise. So to speak to some other research, yes, definitely there is a lot of unknown parameters where that durability is concerned, but it has been tested and we have conducted lab experiments that have demonstrated that the durability of regolith as a material for printing small to medium-sized parts is incredibly robust, and we are looking forward to conducting some mechanical properties to back that up as well.
Yeah, that's all good. It's an excellent question. Unfortunately, it was not what I meant. I'm thinking about the machine itself. How much maintenance will that need?
Thank you.
Spare parts.
Yeah, no, for machine maintenance itself, that will be actually quite minimal. And the benefit of being able to print stuff in space is that if something were to break down on the printer, you are able to print a rapid repair part in situ. So if you're looking to replace a broken part on a 3D printing system, you will actually be able to create it on the lunar surface. But aside from that, the maintenance itself of a 3D printing system in space is actually quite minimal. We are going to be looking at mitigating some of the top concerns, which would be things like dust mitigation, solar radiation output, and microgravity impacts on the printing of the machine itself. So it would be rather minute given current industry standards and the technology that we're working with. I hope that answers your question.
Yeah, thank you. And I think thank you for an excellent presentation, and we're looking forward to see if or when this actually gets to the moon and we can see things being manufactured there.
Wonderful. Thank you so much. I'll be happy to answer any other questions that pop up in the chat throughout the rest of today.
That's great.
Thank you. Great presentation.
Thank you.
Thank you.